Okay, I think it's time to get started. So, any questions so far? And yeah, so at the beginning, let's do some announcement. So we will have our midterm on next Thursday. It's the scheduled in the beginning of the class. We said we are going to do midterm on the 8th week, and yeah, that's next week. So next Thursday we will have midterm. And usually the midterm will take place at just at the same place and same time as our regular meeting, except that you will come in and you take a midterm. And the scope of the midterm will be until next slide. So we have a quantum circuit slide. So that's the beginning of having quantum circuit, and the detailed rule will be posted down in there. Okay. Any question? If not, then let's go back to our classical computation. So hopefully we'll finish the remaining quick intro of classical computation and start talking about quantum circuit today. And classical computation, we say the most important part is this asymptotic notation, because in complexity theory we care about how our resources are used in asymptotic. And that's how that means how the resource grows when our problem size go to infinite. And we need notations to express how fast things grows when problem size goes to infinite. And so usually there will be some scaling parameter. Here we use n here. Okay. Usually there is one scaling parameter, is n. And when there is many, then things are going to be tricky, but we have notation for just one scaling notation here, just one scaling parameter here. So everything is scaling with n, and we want to see how different function grows when n goes to infinity. And we use those asymptotic notation to express bounds about how things grows when go to infinity. Okay, so there is a big O notation that people use most, and also people abuse most. So big O notation means that when f of n equal to order g of n, means that basically we think f of n is less or equal to g of n when n goes to infinity. And then the detailed definition here is that there exists some c and n naught, such that when n greater than n naught, f of n is less than equal to c times g of n. F of n is equal to c times g of n. And so we can talk a little bit about c and n naught here. So we have a cut of n naught because we only care about n go to infinity. So that means for small n, that means n less than n naught we don't care about. We only want very big n. Okay. And the way we have very big n is we say we only care about f and g when n greater than some n naught. Okay, and so the idea is kind of like we have f and g, okay, and they can do whatever thing here and whatever thing here, but maybe another arrow here, okay, so we have f can do whatever, g can do whatever, okay, but so maybe this is f and this is g, okay. And so we say when n greater than some n naught, then so maybe n naught is here. Okay, so we want to say n greater than some n naught, then f is less than equal to g. And also we don't care about constant factor. We also don't care about constant factor, so we can give g an arbitrary constant factor advantage here. Okay. We only care about how fast it grows. Okay. So that's a big O notation. And the other way around is big omega notation. It's basically the same thing, except now this g is the lower bound of f. So f of n is greater or equal to c times g of n. when n goes to infinity. And then there is this big theta notation that just means f just means you both say f and g both satisfy big O and big omega. So f of n equal to big theta g of n means that basically when n goes to infinity, f of n is kind of equal to g of n. It means that it's bound between maybe two different C1 and C2. Such that f of n is greater or equal to C1g but less than equal to C2g. Okay. And so the idea is kind of like so maybe when g goes to infinity, you have some C1g and you have some C2g. Sorry, C1 is smaller, so some C1g here and some C2g here, and maybe your f is kind of wiggling in between, but it's always in between C1g and C2g. Okay, yeah, and here I should say C times g. Okay, so that's the three most used symptomatic notation, and sometimes people will abuse big O notation and just when they say f equal to O of g, but they actually means f equal to theta of g. But if you want to get technically correct, then if you want to say f and g are equal, then you should say f and n equal to theta g of n. Okay, and then there is this two less used notation, the small notation and small omega notation. This means that f of n is actually smaller than g of n when n goes to infinity, and or f of n is actually greater than g of n when n goes to infinity. Okay, and and the difference between the small notation, the definition here and before is that now the quantifier between our constant c is different. Okay, so before you just need to find some c such that f of n is less than c of f is less than c times g. But now you need to have for all c, because you want to make sure f is actually less than g. So you want to have f is less than g not just for some constant, you want it to be less than g for any constant. So that means that f is actually smaller than g. Okay, they are just not different by some constant vector. So for example, you can have maybe f of n equal to n and g of n equal to also n, and so this will have maybe let's have this a little a little less trivial. So f of n equal to 2n and g of n equal to 2n, g of n equal to 2n, and then we have f of n is less than equal to 2 times g of n, obviously. And so with c equal to 2, it satisfies this equation here. So we know that f of n equal to order g of n. But but obviously this is not true then. But f of n is not big O of g of n, because this doesn't satisfy for all c. Okay. And so you can have when c equal to 1, then yeah, so we know f of n is not actually less than g of n, because for c equal to 1, then we have that f of n less than g of n is not true. Okay, and so we don't have big O here. And yeah, so similarly we have big omega, small omega. And then we have some example here. I think we run through last time. And so we have 2n squared is order n squared, because the big O notation don't care about constant, so you can just have n squared here. And similarly, this n cubed over 4 log n is omega n cubed log n. Okay. And then we have some example of this small notation. So n squared is big O n cubed, because for no matter what constant c we have here, so even if you have a very small constant c here, when n is big enough, then n cubed is going to be greater than cn cubed is going to be greater than n squared. Yeah. And one thing that we will see a lot is the small notation mostly used is in this small one notation. Okay, so this small one means that this is less than some arbitrary small constant. So you can have 1 over n is small one, because if so 1 here, so that just means that for arbitrary constant, you can find n big enough such that 1 over n is smaller than that constant, and that's obviously true. Okay, and yeah, so maybe this is a better example. So so we have for c, then we want 1 over n is less than c, and so we just have when n is greater than this 1 over c equal to n0. So we know if n is greater than 1 over c, then 1 over n is going to be less than c. And so we know 1 over n is O1. Okay. And then similarly, we have n log n equal to omega n, because log n is always greater or equal to 1. Sorry, log n grows faster than any constant. And also log n is omega 1. Even though this grows very slowly, you can still beat any constant. This thing go to infinity when n go to infinity. Okay, and now we're back to some easier example. So this example, we have that 2n squared equal to big O n squared. And then we just want to find our c and n0. Okay, and yeah, so f of n equal to 2n squared of n equal to n squared. Then we want find a constant c. So c such that f of n is less than or equal to cg of n, and for n greater than n0. Okay, so here we just give our explicit construction. So we have c equal to 3 and n0 equal to 1. And now we know that for n greater than n0, then f of n is well, greater or equal to 0. And it's equal to 2n squared, and it's less equal to 3n squared. Okay. And here we have a small cheat sheet about different classes that usually separate the asymptotic. And so I guess this is a bit of a review of calculus. And we know that the constant is less than, when n goes to infinity, a constant is less than log n, and less than n, and less than 2 to n. And I guess one thing to emphasize here is that this gap is, the gap here is big. Okay, between log n and n to 2 to n is a very big gap. It means that, and and that means that even if you put some polynomial here, so excuse me. So what I mean by gap is big is that even if you put some polynomial over log n, you have any polynomial of log n is still going to less than n, and any polynomial of n is going to be less than 2 to n. Okay, so really, if you can think about and yeah, so really you can think about is your function about polynomial of log n, or is it a polynomial of n, and then you can really tell you are smaller or greater, etc. And yeah, so I think that's about asymptotic notation. And here is a few tricks, and we have that. A few tricks related to calculus. It says that if your f of n equal to theta g of n, this means that when go to infinity, Oh, this is actually not true. This is not quite true. Okay, so let's skip this. This is a bit misleading. Okay, I will check about this later. But I think this is misleading, so let's not talk about this. And this is the end of symptomatic notation. Yeah, sorry for the confusion. And any questions so far? If not, then let's go to complexity theory. And because we are a bit short on time, so let's just do very quick, very brief introduction of complexity theory. I guess the idea here is we just give you some familiarity to some basic names and notations people will use in complexity theory. And yeah, the actual hard part I will leave for you to read the book or other material. But I want to give some introduction about some notation and syntax that people often use in complexity theory. And yeah, so the first notation we have is this, or the first name we have here is this name of decision problem. And decision problem is basically just a problem where the answer is either yes or no. Okay, so you need to make a decision, and this is a yes or no decision. Okay, when people say decision problem means a problem with a yes or no answer. And for example, here is a decision problem. So so we ask is the number 67 a prime number or not? Okay, and so it's either yes or no, and the answer is yes. This is a prime number. Okay, so this is a decision problem. And then the next notation is something very funny. It's called a language. Okay, so obviously language means many things in computer science or in our everyday. Okay, so but in theoretical computer science of this language or so-called formal language is something very funny. Okay, formal language is a subset. Okay, so I guess I should highlight here. Is a subset of a string of arbitrary length. Okay. Okay, and let me highlight here. Okay. So formal language is a subset of strings. Okay, and here we use weird notation. So alphabet just means a collection of symbols, and usually the alphabet. And I guess the most often used alphabet is actually just 0 and 1. Okay, so alphabet is just a collection of symbols, but obviously you can have an example of alphabet equal to A, B, C, such that. Okay, so alphabet is an arbitrary collection of symbols or characters, and but for simplicity, let's just say our alphabet is 0 and 1. Okay. And then we have this weird notation. Okay, here this notation, alphabet to a star means that a string consists of this alphabet of arbitrary length. Okay, so I guess this is a generalization of the notation of sigma to something. Okay, so say sigma equal to 0, 1, then we will have a sigma 2 equal to this in square, and this will equal to any string of length 2. So it will be 0, 0, 1, 0, 1, 1, 0, and 1, 1. And but we have this weird star notation, means that this is a union of everything of of those set of any string of any length. Okay, so this is arbitrary length. You have a length, it's arbitrary length from length 1. Okay, so this is yeah, so this contains like 0 and 1 and 0, 0, 0, 1, 1, 0, 1, 1, and all the string of length 3, 3, 4, 5, all the way to infinity. Okay, so yeah, so language is a subset of strings. Okay, so this is a very weird set. So here we have an example. So we have alphabet equal to 0, 1, and then this 0, 1 to start just means whatever string consider of 0 and 1, whatever binary string. And then we can have a language that represent all binary representation of even number. Okay, so this language L, one possible language L is this set, this infinite subset, this subset of infinite size, that's 0, 1, 0, 1, 0, 0, and 1, 1, 0. So whatever string that ending with 0, this is a possible language. Okay, and yeah, so this is a computer science formal language. It's very different from all the language you heard. It's not a language that you can write any program or write any article. The language is just a subset of strings. Okay, and this is a formal language. And why do we want to talk about formal language together with decision problem? Because they actually have a one-to-one correspondence, very obvious one-to-one correspondence. Okay, so you can just describe decision problem with formal language. And here we give an example. So let's say we have a decision, we have a formal language. Okay. And so we have this formal language that we had before, this even number formal language, 0, 1, 0, 1, 1, 0, 1, 1, 0, so every string ending with 0. And you can just, you can just ask a problem of does a particular string is a particular string inside this formal language. Okay, so this is an infinite set, and you can give a finite input. So you have some finite input of maybe length 1, length 2, and you can ask does this thing, is this string inside this language? Okay, so the question is here, is X inside L? Okay, and then here in this example, you see the correspondence between your language and decision problem. You can just have language here, and then you just ask is an input string inside this language, and I'll give you a decision problem. It's either inside the language or not inside the language. Okay, and here we can see, well, the answer of this decision problem. So we can pick an input. So obviously different input give you a different answer. Okay, and when input is 1, 1, and the answer is no because you doesn't end with 0. And the answer is 1, 0. The answer is yes. Okay, so you can see that this language of all strings of correspond to even numbers. You can ask, if you ask is X inside L, then the corresponding decision problem is you asking is X even. Okay, so yeah, this is the correspondence between decision problem and the formal language. If you formal language give you a decision problem that is you just ask is a string inside your language. Okay, but formal language give you correspond to one decision problem, and yeah. And here we give a harder decision problem. So here the decision problem is pretty easy. You want to see whether the string is even, you just look at the last bit to see whether it's 0, 1. But we can have a harder decision problem, that is if you can decide is a number a prime number. Okay, so you can have your language just being a set of n, where n is a prime number, written in binary. Okay, and okay. And so here it should probably be, again, we know the prime number are this 2, 3, 5, 7, etc. And then you write it either in language, then you just have these numbers, this in binary, and yeah, so etc. 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay, this is L. Yeah, this language in binary bits. Yeah. And but obviously you can also have change your alphabet and have your language in decimal numbers. But yeah, for now let's have our language in binary. Then this language corresponds to testing whether your input is a prime number. Then it's this binary string that corresponds to the prime numbers. Okay, any questions so far? If not, okay, then we have well, a bit slow, but anyway, then we have the next slide of this chapter. That's talk about complexity class. Okay, and now there are a lot of states now. Okay, so we already have language state of language state of strings. Okay, and now we have something called complex class is set of languages, and so what we are thinking is so this is a formal way to define complex class, but we really think a complex class as a set of problems. Right? Remember, yeah. Remember we talked about decisions, this correspondence between formal language and decision problem. Okay, and yeah, and so complexity class really the idea is a set of problems. Okay, and a set of problems that we want to group some problem together because we think they are about as hard as each other. Well, in some sense. And maybe let's give an example. Then one of the most famous complex class is this P class, okay, deterministic polynomial type, okay. And so now we're back to computation. So this complexity class P just means whatever problem that can be solved in polynomial time, okay. And polynomial time means that complexity big O, so big O into the k for some fixed k. Okay, so this k should not depend on your input size. This k should only depend on your problem. Okay, and yeah, so if your if this problem can be solved, or this language which correspond to a problem. Sorry. Anyway, so the name is the language can be decided in this time, which roughly means that the problem correspond to a language can be solved in this time. So those yes/no problem can be solved in this time, and and this time is a polynomial, means that it's order n to a k for some fixed number k, and then we think we call those problems is in P. Okay. So this is a polynomial time, deterministic polynomial time complexity class, and usually we think the problems inside this class, we think they can be solved efficiently. Okay, and obviously in reality there are something that you cannot really solve practically because this k can be arbitrary large number. So say if this k is 1 million, then it's not really efficient, but for theory's sake, we just think whatever thing inside this P can be solved efficiently. And okay, so let's start drawing. And we would like to draw complexity class. So we think well, the words are for problems, and there is some circle here that is P, that's a problem that can solve in polynomial time. Okay, and the next one is this NP, and you probably heard about this in a lot of other contexts. And this N is doesn't mean not. Okay, so this is not NP doesn't mean not P. The actual name is non-deterministic polynomial time, which is not very intuitive. But the actual meaning of NP is so this P still means polynomial time. But this NP is not problem that solvable by polynomial time, means problems that can be verified in polynomial time. Okay, so remember we are solving decision problems. So those problems will have something. Those are decision problems. So those problems have yes or no answer. Okay, yes or no. So some input to the problem will give you yes. Some input to the problem will give you no. Okay. And the NP is a very funny class, such that if the answer is yes, then then it can be efficiently verified. Okay, and that means but we don't go into the detail. We don't go into too much detail of the verify, but efficient verify, you need something else. So you have someone untrusted give you a witness, and the programming that actually try to compute NP can verify that using the witness and convince yourself that the problem, the instance is, the answer is actually yes. Okay, and so maybe let's give example of NP. So. So the answer of so I guess this primality test, the reverse of it is in NP. Okay, so if you ask is okay, although this is actually in P, but this is easy example. So if you ask is X not a prime number, then this can be efficiently verified because you can have a I guess that's not right here. Okay, that's right at the end. Okay. So one example of NP is that you can ask is some number X not a prime? Then you can have a witness that try to convince you that X is not a prime number, and you can have a witness just being two non-trivial factor of X. So we can have witness this P and the Q pair, such that P times Q equal to X. And so you see this can be efficiently verified because it's very easy to do multiplication. So if someone give you this Q and a P and a Q that's non-trivial, and then you can quickly calculate P times Q equal to X, then you can verify that X is not a prime number. Okay. Even though, yeah, so this is an example of NP, this is a verification. You can do this calculation very quick, even if someone give you this witness. Okay. But if you don't factor X yourself, then it might be hard to find this PQ yourself. Okay, and when we drop complex class, then we can have this NP. Then we know that NP are harder problems. So yeah, so complexity series love to draw those complexity graph, and so we have this NP that's contained in P because they are harder than P. And then the next one. Oh, and sorry, and something missing here. But even though you, from this example, you kind of feel that NP is harder than P, but it's actually not proven that NP not equal to P. Okay? So there are a lot of problems that you think is much harder than P that you don't really think you can solve in polynomial time. But complexity theory is very hard, and there is no actual proof that P not equal to NP. Okay? And finally, then there is we'll be talking about time complexity. That is how many times you need to use to solve a problem. And there is also complexity about space, and that is P-space complexity. And that's basically all the problems that can solve using polynomial amount of space. But I guess special thing about here is that when we talk about those space complexity, and we will put no restriction in time, so you can use a polynomial amount of space and whatever time you like. And it turns out that the P-space is huge. Here we won't give proofs, we'll just state the result. P-space is really large, P-space. Okay. So it turns out P-space is huge, and it also contains NP. And later we'll see in our quantum complexity that the P-space also contains efficient quantum computation. Okay, and yeah, I guess this is all I want to say for now. So P-space is a really large space, and it contains NP, and but even though you think P-space is very large, we still don't know whether P-space equal to P. Okay, so this is also still, although you think you feel that P-space is a lot larger, a lot more powerful than P, but we don't have a concrete proof that P-space don't equal to P for now. Okay. Any question? This is a very brief introduction to complex C class. And I think this will be end of what we want to say about classical computation. And want to hurry up a little bit and let's go to quantum computation. Okay. And so finally we will go to quantum computation now. And now we talk about quantum circuit. Okay. And excuse me. Let me change the video. Okay, yeah, quantum circuit. So this is a bit of a weird merge between chapter 1 and chapter 4 of the textbook. Okay, and yeah, so let's go to quantum circuit model. So quantum circuit model is kind of like a classical circuit model. You still have the two elements that you see in classical circuit model. That's qubit, that's those wires and gates. And so each wire now, instead of one qubit, instead of one classical bit, it basically usually carries one qubit. Sometimes people will merge more qubits together to one line, but usually one line means one qubit. And just as a reminder, one qubit means two-dimensional quantum space. And so one qubit is a two-dimensional space, and usually it has two basis vector k0 and k1. Okay, and then we have gates that for the quantum operation you can do, and they are unitary operators. So here we have some possible gates. So the H is gate, Z is gate, and here we actually have two qubit gates here. Okay, this is how we write the control now in our quantum circuit. So this is actually a two qubit gate. And obviously you can have other kinds of 2 qubit gates or even 3 qubit gates, etc. Okay, but yeah, anyway, you can put gates on your quantum circuit. And so this headmark is a gate, this is a gate, and this C naught is a gate. Okay, so you have the wires that are qubit and the gates, and then there is something you don't have in classical computation, that's a measurement. Okay. And measurement is a weird thing, and okay. So this is what we mean by measurement. Okay. So yeah, so this thing is measurement. What do we mean? And when you put the measurement on some wire, it means you measure this wire. Okay. And because the wire is usually a qubit, so measurement will give you a 0, 1 outcome. Okay. So here we have we use one line. This is a single line to mean quantum wire. So this is one qubit, and we will use this double line notation to mean classical information. Okay. Actually, yeah. So we use double line to mean classical information, and so basically this is 1 bit. Okay. 1 bit. And as in classical circuit, the time flows from left to right. So you have input state here. So usually it's all 0, but obviously you can have a different input state. So you put an input state. So these 3 qubits are all initialized into the 0 state, and you go through the gate, and then in the end you will measure some of them, and you will get some classical outcome. That's usually what the quantum circuit do. You start with 0, and you do some gate in between, and maybe you also do some measurement in between, and in the end you will get some output. Okay. And let's go back to talk a little bit about the quantum gate. And so different from classical circuit, one difference is that there is no fan out. Okay. So this is coming from no coding theorem. So remember, in classical computation we see that we can fan out, so we can have 1 bit split into 2 bit, but that's not possible in quantum because there is no cloning theorem. So you see that actually a number of qubits in the circuit is kind of preserved until you do measurement on some circuit. Okay. Yeah. So, but anyway, you cannot split 1 qubit into 2 qubit, copying that because there is no cloning in quantum in quantum mechanics. And also, one interesting thing is that every gate here is reversible, because we know every gate is a unitary operator, and we can always reverse the operation of 1 qubit of a unitary operator, because you apply unitary, you can apply the inverse of the unitary. There's a U dagger, so you can always reverse everything you do on the circuit by just apply the inverse of your unitary. Okay, and this is actually different from usual classical computation, because a lot of gates in classical computation is not reversible. Say classically you have the AND gate, right? And of x1, x2. Okay, and the AND gate is not reversible because it gives you 1 bit. Okay? You have 2 bit in and you have 1 bit out, and it's not possible to reverse this. Okay, and so you see that you need to do a bit different in quantum circuit, because some classical gate you use is not reversible, and the quantum gate are always reversible. But it turns out that, okay, so that's, we'll digress a little bit. It turns out that this is okay. You might think that the AND gate is not reversible, and that means maybe quantum circuit cannot do classical computation. But it turns out that you can just have a little bit of blow up, and you can still do all classical computation using the reversible gates. Okay, and yeah, so that's fine. Reversible quantum gates. Okay, and let's go back talking about more quantum stuff. Okay, and so now we give you a lot of notation. So most of the gates you have here you have seen. So notation for some gates that we mostly use, and so first of all, you should be pretty familiar with our favorite polys and the hidden market. Okay, so poly X once again is 0, 1, 1, 0 matrix, and we just draw it as a block and X. And poly Y is just a block with Y. It's 0 minus I 0. And poly Z is 1, 0, 0 minus 1 gate. And we have hidden market. That is 1 over square root 2, 1, 1, 1 minus 1. Those are all 1 qubit unitary, and these 4 of them you should be very familiar now. Okay, and yeah, and you should really memorize all 4 of them. And then there are these other 2 that's also good to know. Okay, one of them is the phase gate, and it's basically a square root of a Z gate. It is 1, 0, 0 I gate. Okay. And then there is also this pi over A gate or T gate. That's sorry, I think we have a typo here. That's a square root of this S gate. Okay, so this is not. So T gate is this gate. This 1, 0, 0 e to the I pi over 4 gate. Okay, and yeah. So S gate, phase gate, S for phase, and T gate. T for other reason. Okay, it is called T gate or pi over A gate. Okay, so we have those 1 qubit gates that are mostly used, and we will that often that are used a lot, and we give them their own notation. That's kind of conventional, and yeah. And I guess one more thing. So is phase gate. We use our notation S here. But in the literature, sometimes it also because it's called phase, and so sometimes people also call it P gate. Okay, so yeah, sometimes P is P for phase. Okay, it's just notation. And then we have 2 qubit gates. 2 qubit gates are a little more interesting, and I think you should also memorize. So those 2 you should memorize. There's a CNA gate here, and control Z gate here. Okay. So hopefully you should memorize these 2 notation. And so CNA gate we see a lot, and I think we already talked about it a little bit in classical computation and also in other contexts. And if you write out, it's a 2-qubit gate. So if you write out its 4 matrix, it is huge matrix. That's 1 1 and 1 1 here. And a more structured way to see this is diagonal. If you think this 4x4 matrix as 4 2x2 matrix, and then it has this upper left block as identity and the lower right block as x. Okay? So in this notation, we means that each thing here is a 2x2 matrix. So it's identity 2x2 matrix and 0 matrix, 0 matrix, and x 2x2 matrix. And really this is a classical gate, and so it's defined by how it acts on computational basis. And on computational basis, it acts as a classical CNOT, means that if you apply a NOT gate on second qubit, if only if the first qubit is 1. Okay, and so that means that if the first qubit is 0, then you do nothing on the second qubit. And if you first qubit is 1, then you add 1 to the second qubit. And you can actually have a very simple way to write what you do to a computational basis. There is the first qubit will stay whatever it is as the first qubit. And okay, so let's say it's AB computational basis. So if you input AB in computational basis, then if A is 0, then B stays the same. So so that equal to A is A XOR B. Okay, and if A is 1, then B gets plus 1, get not get. So B become B plus 1, and 1 equal to A, so that's still A plus B. Okay, and yeah. So I give a very quick verbal proof that you apply a CNOT gate in this AB state, then output will be A and A XOR B, or A plus B. So this notation, this plus circle means XOR, and yeah, this A plus B means A XOR B, and is equal to 1 if only if A not equal to B, and I guess it's easier to say this is the usual plus, so A plus B and mod 2. Okay, so it's equal to 1 if only if A not equal to B, and A equal to 0 if only if A equal to B. Okay, and anyway, so that's a CNOT gate, and then we have a CZ gate. That's very similar to CNOT. It basically means you apply the Z gate on the second qubit if only if the first qubit is 1. And so once again, it does nothing when the first qubit is 0, and apply the Z gate when the first qubit is 1. And you write down the diagonal matrix, it is 1 1 1 minus 1. And interesting about this Z gate is you can check that it's a symmetric between first qubit and second qubit, means that if you control on second qubit being 1 and apply Z gate on first qubit, it's still the same gate. Because you look at this, you see that what this thing do is that you apply a -1 phase if only if both first qubit and the second qubit is in the 1 state. Okay. And yeah, and so what this do is you can think about what you do on computational basis, and so you can have control Z on AB. This will equal to -1 to the AB and AB. Okay, so you get a -1 phase if only if both A and B equal to 1. Okay, and because it's symmetric, so actually we give it this very symmetric notation. It's kind of funny. It's a gate with 2 control register. Okay, so this gate with 2 control register means control Z. Okay, and we have like 1 minute, and I guess we can say one more thing. Okay, and then we also have a general control unitary gate. So if you have arbitrary arbitrary unitary U, and they want to have a 2-qubit version as a control U version. The 2-qubit version control U, and then we will write it this way. So we'll have this solid dot here and a line down here. Then to this U block, this means that this U is control on this first qubit. And so you have a computational basis A here and the arbitrary state psi here, and it goes through this control U, then you become this first control qubit is still A, and you have a U to the A times psi here. Means that if A is 0, you don't do nothing. A equals 1, you apply U here. Okay. And I think we are out of time today, and so we'll stop here. And on Thursday, we'll finish this slide and talk a little more about other things. And and I guess the plan is that next Tuesday we'll have a small review, and next Thursday we will have our midterm. Okay. If no question, then that's for today. Okay. Thank you.